Okay, so this is my third alum video, and they have grown plenty since the last time. They were set on the room on January 23rd, and they're bigger now. They're still slowly evaporating. They're by the window now, and the weather was warmer, so the water was evaporating. These are pictures of the crystals. As can be appreciated, they're like pretty big and pretty solid at the bottom of the vial. And in order to make one big crystal, the process that needs to be made is to take one of the smaller crystals that's already formed at the bottom of the vial, which is called a seed crystal, and set it in a saturated alum solution, and set it somewhere with a very constant temperature, and cover it enough so that none of the dust gets in, or like no pollution from the air. And basically this will cause if it's saturated, it will create like the equilibrium to go towards the alum crystal, and so the alum crystal will start growing, and there will be one big chunk instead of like the smaller seed crystals that are in the bottom of the vial at this moment. And it is important not to let the seed crystal, touch any of the walls of the container, because it will not grow then. So it needs to be hanging with some sort of string. Now, regarding the importance of despacing, it is important because of X-ray diffraction. And X-ray diffraction is the way to understand the distance between the neighboring planes. So since we're looking at a crystal lattice, there's like different planes within the crystal, which are separated by a distance d. Like the distance between one of the planes and the next one is d. And basically, by understanding this distance and the angle between the planes, the entire crystal structure can be understood and drawn and constructed. And so, by Bragg's law, which will be explained in a bit, and having a device that like detects the angle at which the bigger intensity occurs, which is precisely when the path length is of integer, then the structure can be reconstructed. So basically Bragg's law says that n times lambda equals 2d sine of theta, where theta is the angle at which there's a high intensity. In this case, it is of 21 degrees. 2 theta is 21 degrees, so theta is 10.5 degrees. And lambda, which is the wavelength of the X-ray used, is 0.15418 nanometers, and n equals 1 because there's no path difference. So by isolating d, we get that d equals 1 times 0.15418 nanometers over 2 sine of 10.5 degrees, and that equals 0.423 nanometers, which is in fact the difference between neighboring planes in the crystal lattice that is being studied.